In this video we're going to see why each of these three different metric relations are true, and we're going to use the same idea to prove each one. The idea is we're going to show that the three triangles in this diagram are similar. So we can see if we call this angle alpha, then this angle here, if we consider triangle ABD, must be equal to 90 minus alpha because those two angles are complementary. Also, the angles at angle A are complementary, so we know that this angle DAC has to be alpha. And by the same reasoning, this angle here is also 90 minus alpha. So, rather than write out the notation for each triangle, let's call this triangle triangle 1, triangle ADC triangle 2. Just to be clear which ones we're talking about here, I'm talking about this triangle here. The blue triangle is ABD, and we have also a third triangle, the large triangle, ABC. So all of these triangles are similar because they have the same angles. So let's just quickly abbreviate this here. Triangle 1 is similar to triangle 2, which is similar to triangle 3. So any combination of these are similar, and these results come from the ratios of that similarity. So let's first compare triangle 1 and triangle 2. So in this ratio in triangle 1, we see that we have H here, H, and what else appears? P appears in that triangle. And P, so that's our ratio there. And we can see that H is opposite, H here is opposite to angle alpha. So let's just make a note of that here, alpha, and P is opposite to the angle 90 minus. Now, just to make that a little bit easier, let's call 90 minus alpha beta. So if we undo those, this angle here was opposite beta, and compare that to triangle 2. Now, the angle opposite, the side opposite angle alpha is K. So if we write that in, K, and the opposite to beta would be H. So we have now our ratio. If we simplify with cross multiplication, we've got H squared equal to P times K, and the result's shown. Oh, by the way, we didn't say the reason for these similar triangles. Now let's consider triangles 1 and triangle 3. So in this, let's see what we've got. We've got C in triangle 1, and also P here in triangle 1. So let's use that ratio C over P. Again, we'll choose the opposite angles there. For C, it's opposite to the 90 degrees. So we've got 90 there. P is opposite to beta. So let's relate that in the large triangle here. Opposite the 90 degree angle here would be this whole side here, which is P plus K. So we'll write that there, P plus K. And opposite the 90 minus beta, we can see the opposite side is C. So we'll write that in our ratio. So now, simplifying, cross multiplication again, C squared is going to be P plus K times P. And I've run out of room there, but it's important to notice here P plus K. You notice here that that's written as A, and the reason is because that's just the notation that we use for the side opposite to angle A by convention, so that's why this can also be written as P times A. Now the last ratio here that we're going to show involves triangles 2 and 3. So 2 and 3. Now let's pick some information in the red triangle. Can we see B? Yep, B. And we see also K. So B over K. Now let's look at the opposite angles. B is opposite to the 90 degree angle. K is opposite to alpha. So let's write that in. Alpha. That should be 90. Equals. Now in the green triangle, the 90 degree angle, well, that opposite that was P plus K. Let's just erase that from the diagram. P plus K. and opposite k, we'll see, opposite alpha, we'll see that the side we want is b. So when we write in that into our ratio, cross multiply again, we have b squared equal to k multiplied by p plus k. Again, p plus k can be written as this side length a. I hope you enjoyed that.